All right.
All
Welcome
right,
to the Mr.
you're
Bill
recording.
podcast.
Thanks very much for having me, Mr. Bell. It's my pleasure indeed.
Yeah, it's nice to finally connect. I've heard a lot about you over the years from various people. Deadmau5 was big upping you to me at one point, and my buddy Chris Hector, who works at Sequential,
Oh, Chris,
he
yeah,
was,
yeah.
yeah, he was big upping you as well.
Yeah,
And
Chris is
I
a great guy. He's done some great stuff.
yeah, he did a lot of work on the Pro 3 and I believe some other sequential synths as well. Yeah, I lived with him for a while actually in San Francisco, and so I got to have access to like all the sequential shit for a while, which was nice. And
Yeah, it's
kind of,
funny, like in plugin land, us developers might complain about, the pain of different doors and things, but I mean, he's in hardware land where you don't have a door. You got bare bones, and you've got to write the operating system and customize it, and it's a whole different level of pain.
yeah, I imagine like there's no framework to work off. You kind of got to build the entire thing yourself.
Yeah, yeah. I mean, but it's then you're in control, right? Then you get to call the shots. Run at whatever sample rate you want, do whatever processing you want. Nobody's there to interrupt you. It's
Yeah,
yeah, it's good.
maybe it's just so you're just like front loading the stress. There's a ton of
Yeah, yeah. Once you got that sorted, though, then you can really stretch your wings and do stuff until like that hardware is obsolete, and then you got to do it all again for the next like latest chips and stuff you want to do.
right. So yeah, I didn't realize you're Australian. Actually, I didn't consider where you were from, but I just didn't expect Australia. I only found this out, I think, last night when I was reading some interviews to try and like prepare for this.
Yeah,
And
yeah. Based in Perth, Western Australia.
nice, yeah, I've been there a couple of times. I really like Fremantle. It's a really nice little spot.
Yeah, we're just walking distance from Fremantle here, just up the road in White Gum Valley. So yeah, it's nice to be able to walk down there and catch up with friends and do whatever, and then just kind of stumble home.
Yeah, it's a good little spot for bar hopping and stuff like that. I think I remember one day there. Have you ever been to the Little Creatures factory?
Oh yeah, yeah,
Yeah, that
yeah.
spot's
Lots.
sick.
It's quite family friendly as well. So they got the sand pit out the back, and it's beautiful. On a summer's afternoon, it's a gorgeous place to be.
Yeah, like right on the water, and I think do they brew everything there as well? I'm not sure.
They do. They've got like next door. They've got the actual main brewing. You can actually go and squeeze there and have a look and see the giant tanks. And there's so many different places to go. It's awesome.
Yeah, yeah, that area is really cool. It's cool that you're really close to there. Nice spot to be to balance out the solitary confinement style work of programming, which I kind of
It
have as
must be
well.
the same for you, right? I mean, you're like when
Basically.
you're working. I've listened to your tracks, and they're pretty intense. There's a lot of attention to detail. There's a lot of production. There's a lot of effort. It shines clearly through. So, I mean, you must be doing some insane hours to pull that off.
Yeah, exactly. Yeah, it's a lot of hours for a lot of months in a row to like produce, a 10-track album or something.
Mm.
A lot of not going out of this room, which is um but that's what you got to do. I mean, like I when I first started making music, I was always like, oh man, like I really like this attention to detail type music and I love the
Yeah.
results, but I really don't like how long it takes.
Yeah.
And but I don't know, I've kind of just accepted it's just part of it now. I like the results enough that I think it's worth
They're
spending
always,
that much
oh,
time,
it's so worth it. Please keep on doing it.
which I imagine you probably feel similarly about modeling hardware, right?
Yeah, it does get pretty intense sometimes for what I suppose. I mean, you do hear the results as well at the end of it, but yeah, there's a little slog sometimes, and sometimes you get caught up on things that you didn't actually think would be too hard, and a couple of months later, you're still scratching your head and going, "Well, how do I actually get this right?" And moreover, like you can solve a lot of these equations, but that's not much use if half your CPU's gone on one tinsy little thing because it's really hard to solve.
Right. But well, before we go any further,
Yeah.
maybe you should just explain a bit about who you are and what you do. Because from my perspective, you're like one of the DSP guys. There's like you and Dave Gamble, in my opinion, are like the sort of top two like analog modeling guys that I know about anyway. And you were responsible for the glue compressor in Ableton, for example.
Yes.
Like from what I understand, you made a plugin called the Glue, which is like a compressor model on something else, and then Ableton was like, let's put it directly in Ableton, and then
Yeah, they were struggling for. I think their customers were wanting some higher quality bus compression, and they saw the Glue and liked it, and everybody was into it, and so they got in contact about licensing that. So we did that. So yeah, as a little kind of rundown of where I'm at. So I kind of started working out in a few different industries, but doing kind of signal processing, and but I've always loved audio, and so during my university years, got into playing in bands and using trackers, actually, which I heard on one of your previous episodes. You mentioned
the
Fast Tracker
Polyend.
2. Yeah, the Polyend is the new stuff, right? And it's great. I love seeing that.
Yeah, I'm a big fan of the Polyend tracker
Coming out, and and it does have the vibe of the OG kind of trackers, but this was on a computer. So this is Octamed Amiga days and Fast Tracker 2 on PC, when PCs could barely, you had to have a sound card that you put in. They didn't have sound by default. You had to buy a sound card and add it, and then and then do your tunes. And that was so much fun. The direct contact with your samples, and just that really it's kind of like a guitar for samples. Your fingers are on each string, and you can just mess with them as much as you want and trigger anything. And it's so direct and fun. But then, after that, then so I was studying maths and computer science at UWA, University of Western Australia, and just got into audio programming because Steinberg had just released the VST SDK version 1. And I grabbed a copy of that, and a friend of mine, Scott, and I, who was at St George's College at UWA, we both just started programming. We were both programmers studying computer science, both loved audio and trackers, and suddenly we could program anything we wanted. And there weren't hardly any. We released some of the first VST plugins ever available. And that was through our combined outfit called Velaset from the Clockwork Orange. And so we released that and got loads of hits on our webpage because Steinberg had linked directly through to us. So we're like, whoa, why is this spike in traffic? What's going on here? And they'd linked through to us, and then kind of gave us copies of the latest versions of Cubase and wanted more stuff to happen. And so we that took it from there.
So you ended up building like plugins for Cubase as well?
No, we didn't actually. These were all third party, so they had their own DSP engineers and they were doing their own thing. But the first one that we did was so a very early version of V-Filter, and a really fun slicing kind of one called V-Reorder, where it was like a buffer stutter plugin with a delay built in, and so you could rearrange each slice, reverse slices, pan them, volume stab them, and then have a delay feedback. So it kind of makes these polyrhythms coming through.
It's kind of like gross speed or something like that.
Yeah, I have lost track of the stutter stuff. This was before stutter stuff existed, except for like Aphex doing it manually, or there's like laborious, or what was the thing? There was like this box of nodal goodness that people used.
Kyma.
Yeah, that's the one. What? Yeah. Kyma DSP, Kyma something. I can't remember.
Yeah, they made like the Capybara box or whatever.
They made some fairly expensive and bespoke DSP boxes, which no way I could afford that. But hey, I could slice up my vocals or anything in real time now because the VST SDK came out. Yeah, so and then from there, just like to really high level. So I was still kind of working other jobs, and then but really got more into coding DSP, and was a bit daunted by setting up the whole e-commerce thing. Web pages didn't exist that you could Like, the engines that are around these days, you can,
Yeah, there wasn't
sell
like
anything.
WooCommerce or
No, that
Squarespace.
didn't exist. It was like you talk to a bank and you spend a lot of time coding, and it was just painful. So there's a guy, Angus Hewlett, in London, who had a company called F Expansion, and he'd gotten in contact about working on a project that I turned down. That was BFD, which is a drum multi-sampler.
Yeah, it was like the original Superior drummer or whatever.
Sorry?
It's kind of like the original Superior drummer. Or
yeah, that's the one. Yeah, and that was actually Steve Duda's invention. He approached F Expansion, then Angus approached me to program that, and I said, "Oh no, but I've got my friend Scott who would love that." And then I joined over with them a bit later and worked on a bunch of other products, and then started Cytomic myself, and then released our own products, did some licensing deals with Ableton, and here we are.
Yeah, I was actually in I'm in a few different like group chats with just producers and stuff, and last night actually I looked in one of them and someone was like, "Oh, Live 12.2 just came out," and then they were like reminiscing on like, "Man, I remember when like way back in the day, like there was that version of Live that came out where EQ8 just like got way better overnight."
Suddenly didn't sound,
and like you would open up like old projects and they would all just sound a lot better because like the EQ8 had been upgraded, and that was in large part due to your DSP, right?
Yeah, that's right. So all right, so there's a good story on that one, which is, so the Ableton wanted to license the glue, and they wanted to put a sidechain EQ on it, and they had EQ8, and they said they were going to use that, and I said, "No, you're not. It sounds bad. I don't want that even on the sidechain on my compressor. Thank you very much."
Fair enough.
Use this instead. And I'd already worked on these algorithms, which I provided through technical papers online, making them public knowledge, because there's this, I don't know, it's like, I think it's a non-issue these days. It's still around a little bit. There's something called a direct form 1 biquad filter, which is digital trash, and it breaks really easily because it abstracts itself away from an actual circuit. And I understand why they were used. They're like kind of the most efficient structure, but there's better ways to do it and support audio rate modulation and have no numerical issues, so that when you're at low cutoffs, it suddenly turns into garbage. So like in the high pass filter in EQ8 added rumble. It didn't cut rumble at low frequencies, it added rumble, like an audible rumble as well.
I remember noticing this, actually. I remember when I was in college and a professor of mine opened up, I don't even think it was Ableton, I think it was like Pro Tools or something, and put an EQ on something and cut he had something in Pro Tools that was 0 dBFS, and then he cut on the EQ, and then it started peaking, and he's like, "I'm removing shit. Why is it peaking?" And like the point of that exercise was to like impart on us that like not all cutting equals down.
Yeah, but it should. Okay. No, what they might have been talking about is when you have a transient go through a high pass filter, if you remove so say you have a square wave, right? It's of a certain amplitude, but the rising, and that would be, let's say plus or minus 0.5 square wave, like in amplitude. Then if you high pass that enough, the jump plus or minus 0.5 becomes 1, if you know what I mean, because it's filtered away the DC, and then the jump between what was minus 0.5 is now 0, but the jump stays because that's a high frequency. So now you're up to 1. And then you'll go down to 1. So you've actually doubled the dynamic range that you're taking up by high pass filtering a square wave. So yeah, that's but you know what, I think in analog land you do that and then you clip off the tops and everybody's happy. It still sounds good.
Yeah, I don't think I will. I've tried to grok this so many times, and I've tried to look into fur filters and all sorts of different like responses and look at like images and graphs of like how this fucking line goes into this thing, and I cannot understand it for the life of me. I think you need to like deeply understand math to understand why this shit happens.
Oh, Yeah, there's some things which are definitely tricky like that, but I think a high pass filter is just one of those things that you have to understand that the jump between low to high doesn't go away.
You're talking about low frequency to high frequency, or are you talking about 0 to 1, like the compression to rarefaction?
So if you imagine a square wave, and the two edges of the square wave have a total length of 1 each, like from
In
plus
height.
5 in
Like
height, yeah.
vertical height. Okay, yeah.
Vertical height, yeah. So if you imagine, and that jump is a very high frequency. It's at the top of the range. It's like that's buzz from that jump. Do you know what I mean? Like a spike, a very spiky, impulsive thing is a very high frequency thing. The actual holding it for a while is very low frequency.
Yeah, maybe that's where I'm getting confused, because I always thought frequency was like temporal based. It's like how many times per second a thing happens, right?
Yeah. So if just imagine having like a spike play and you just hear this click, right? This tinsy little click. Now, the faster you play it, the higher a frequency tone you could hear. But if it's like just click, 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 then that would be like, a low frequency. So how many times that click happens is kind of the frequency, but the kind of the base bit of it is how much does it stay high for that time. Like if you imagine a sine wave, that at that frequency is kind of a pure, it doesn't have the high frequencies of it. It's just all rounded off and smooth. And if you take away that holding away from 0 from it, you're just left with the click. But with a high pass filter, when you're doing that, you are left with a click that's kind of twice as high as it normally is, because it's shifted the whole square wave up, and the length between the bottom and the top still stays. So anyway, it's probably easier to look at some plots and not on a, sorry for wasting that time on the podcast, but yeah,
No,
you can actually.
I'm interested in hearing how you think about this for sure.
Yeah, you make when you high pass filter, you can make things have more of a spike to them. Like they actually get taller and lower. But with the coming back to the Ableton filter, it wasn't that it was doing that to make the low frequencies kind of bigger, which it doesn't. It should cut them. It actually, because of numerical issues in the algorithm, was a noise generator that made like brown noise, really low frequency noise that it just added to your whole mix. So you go to try and remove some rumble, and you're just adding noise as rumble. So it was, so anyway, we got that one sorted, and I have made this algorithm public. It's used in hundreds and hundreds of different synths and EQs and things around everywhere. And I'm happy for that, because I really don't want direct form 1 biquads around ruining everybody's day. And the other side of them is when you modulate them. So if you have the high cutoff and then sweep it down really quickly, they don't do what an analog filter does. They have this abstraction of the structure, and there's little rounding errors that happen because you change the cutoff on it. It's expecting the cutoff to be the same the whole time and never change for the algorithm to actually work. And that doesn't happen in audio. You're modulating this even at audio rate.
Automate things and
Yeah. And as soon as you do that, that algorithm dies. And with the state variable filter analog model, which is like what do you call it? Like in analog modeling, you can do kind of pure analog models. You can just make it ideal. Like no circuit could be that clean, but you can do it because it's just maths. And there is a bit of rounding error due to actual floating point or double precision arithmetic. But the theory is very pure, and you can actually get a way more pure result from doing digital processing with a filter. You can have zero distortion, zero audible distortion. And so this algorithm, you can sweep it from as high to as low as you want at audio rate, and it'll all behave perfectly. There's no extra thumps or energy conservation that's not working, and like adding weird sounds. I mean, maybe you want a weird sound sometimes, but most of the time, that should be optional.
What was the process like for getting the glue and EQ8 in Ableton? Did you said it started with the glue, and did you kind of like write the code that would go into that, or did you kind of just give them your code and then they adapted it into an Ableton plugin and then you kind of used an alpha version of it and yes or no things, or like what was that workflow?
Yeah, so I'd already written the plugin, and the DSP is pretty clean. So there's a very clean API. So it's a completely standalone class in C++ land, which is the kind of code that it's written in. And they wanted in the contract a lot of time to integrate the code, and I'm like, sure, add as much time as you want because it's going to take you a day. And they got the code and they went, oh yeah, that's okay. So, and then we just started working on the user interface. And what I wanted there was, I really like these old compressors. They only have a couple of knobs and, big VU, and they're kind of dumb, right? They're so approachable. They've limited even the clicks that you don't want. Every time you're making a decision,
it forces
you're kind of like wasting time. What's that?
I agree. I like these. It forces you into a decision. Yeah,
exactly. And it's like, click, oh, that's too fast. Click, oh, that's too slow. Click, oh, that's in the middle. It's like the Goldilocks, like you can dial in the Goldilocks way quicker.
Right.
And so that needed to be there on the glue. And then what I wanted was space, because the Ableton interfaces are very cramped. So I wanted them to actually just space out the controls a bit, have a big VU, have two big knobs, and then, the other ones not all crammed. We're not trying to optimize space here. There's it's fine. And hopefully that comes across when people use it. You just feel a bit easier and it's like, a bit more relaxing, and you can just dial in and off you go. So yeah, the process was actually pretty easy. They showed me a mock-up of it, and I said, more space, and they did that. And but the guys are good at Ableton. They are meticulous with what they do. They're very careful. They think about a lot of things and they're trying to be minimal. But I was like going, yeah, we can be even more minimal.
Right. Nice. And I guess EQ8, like the UI already existed, so you just gave them your filter code that was going in the glue anyway for the sidechain component, and they just adapted that to EQ8.
Yeah, so I gave them the algorithm, which is easy to implement. I like so I publish papers and just have something called pseudocode, which is each of the lines of the algorithm in generic maths that then you can implement in any programming language you want. And so I gave them that. They had what I gave them actually more specifically was a 2-pole SVF. So that is what do you call it?
Like a 12 dB.
12 dB.
Yeah.
And you can change the resonance or damping as it is in a state variable filter and cutoff. And you've got 3 mixing values, which is your high pass output, the band pass output, and the low pass output. And you can mix them all at once to get all the different responses that you want. And so that's all that I provided, that core code, and also the translation from their existing coefficient calculations to these analog ones. And they did all the spectrum analyzer, all the drawing of the curves. So they could reuse that same drawing of the curves because it's the same shape. And they did all that, and they came up with, they have existing code that they needed to maintain compatibility with, but suddenly you can just swap in this thing, which suddenly is super clean and doesn't add rumble. And when you modulate it, it doesn't do weird stuff.
Do you think, you said prior to sort of when you made these SVF filters that were really clean, that everyone was kind of using these bi-quad filters, which were bad because I guess they were just like easier on the CPU and you could run them, but they came with like some trade-offs. Do you think that we about switched over to the good filters when computing got good enough, or do you think we were on bi-quads for way too long?
Oh, we were on them for way too long. I remember it was hilarious. I read this hilarious if you like reading technical papers, like but there was this in a paper, in the Chamberlain state variable filter paper. So there's another form of filter which has got used a lot in the early Waldorf stuff, definitely the early Roland synthesizers, the JV1080s and all that kind of stuff, called a Chamberlain SVF. And there's different types of, when you model a circuit, you can do different things. And you can, when you've got capacitors, you have to kind of add up the energy that changes over the capacitor, actually the current that is over the capacitor, kind of it integrates current. And how you integrate, you can do it in multiple different ways. So you can either take into account, the two main mathematical terms for it, and sorry to get a little technical, is the explicit and implicit versions. Explicit, everything only depends on the previous sample. The implicit ones, they solve for the current sample and the previous sample or previous multiple samples. And that might sound like, oh, how can you solve for something that you need the output of now in terms of now? But it's pretty straightforward in the maths. It's if the equations are linear. So so technicalities aside, you can solve for it, but you need a division. So yeah, maybe that's for anyone that's vaguely into maths that would know their high school maths, which is a line. The equation of a straight line is y equals mx, m times x, m is the slope, plus some offset b. So in these kind of equations, and in most more kind of advanced circuit modeling, we're solving for the x. So you've got the x on the wrong side. You need x equals something. So you subtract the b from both sides. You've got y minus b equals m times x, and then you divide by m, and there's your division. So now you've got x equals y minus b all divided by m. And previously, so the real turning point is now, when you're cooking your filter coefficients, you have a division. And so if you want to modulate per sample accurately, then that's like at least one division per block or one division per sample. And that used to be expensive until floating point computers got better and better at division, which they are really good at nowadays. And I'm very thankful for that. So thank you for everybody in like games and engineering and everybody wanting fast division, because it means that audio circuit modeling is a lot easier.
There was this argument that I used to see online a lot, which I don't see so much anymore, which was people like complaining about summing in Ableton. And the way that I've always thought about this, and I don't know if I'm wrong, but you probably will be able to tell me, is I would figure like if you're adding up like one waveform and like two other waveforms, you're just doing like 1 + 2 + 3 equals 6 or whatever.
Yeah.
Is it that simple, or is there some like crazy shit to summing that's it's that simple?
It's that simple, yeah. So it does get, so I have to deal with a slightly more complicated case. You can engineer, you can do deliberately obtuse things to break simple summing. Most of the time using what's called an FP32, which is a 32-bit floating point number. And that has some, a bit which is like a power bit, and then a bit which is the precision bit. And the precision bit, are normalized between 1 and 2. And they're like the fractional bit, and then the scalar bit for it. So you get these terms which it ends up being 23 bits of precision and a whole bunch of exponent, which means that those 23 bits can be way up and way down in value. So if you have the worst case for this kind of a number is when you have a big DC offset and then a tinsy little signal wobbling up and down on it. And then, so what happens is all the precision of holding this DC offset gets chewed by that. And then your actual signal, which is wobbling up and down, has no precision left to actually represent it. So it'll be like these last few bits. And then when you take away the DC offset again, it'll scale it back, but all the bits are gone. So it's like you've lost most of your signal. So yeah, you can engineer these situations where you'll hear crunchiness and you've lost bits. But for most audio signals that aren't riding on huge DC offsets, and I'm talking about way more than plus or minus 1, which is the standard audio range. It's like, up around higher than that. And mostly you're not doing that anyway. Like there aren't that many frequencies that are just sitting almost near your floating point, like the plus or minus 1 of a standard DAW signal. So there are some cases, and you can get slightly better results using 64 bits for your floating point number in the summing side of things. But most of the time it doesn't really matter.
Right. And so, like, I've had a bunch of people at this point tell me that when they sum stuff through the metric halos interface, that it sounds like noticeably better. Is this a real thing? Because I feel like I've done this before. I've summed shit through a metric halo and it sounds the exact same to me.
Yeah, I would. The thing is, it has to get to the metric halo sound card. All right. So, are you talking about turning it into analog and then back into digital, or?
I'm actually not sure if when it goes through the metric halo, like you stem it out of Ableton or whatever, and then you import these stems into this software that I believe might be called Mio, and then you sum it together in Mio or whatever. It might even be a real-time process. But yeah, from memory, I couldn't hear the difference. But I've been told by a lot of engineers, a few of who I think have a really good ear, that it makes a big difference.
Yeah, well, if you're using most of the signals that an audio card can play back, it's about 22 bits at best. I would say 20 bits of actual signal, not in hiss or noise. And a floating point number, which is what you're dealing with by default in live, has 24 bits of precision, basically. And then way more dynamic range than that. So in other words, if you've got a really quiet signal, it'll still be 24 bits of precision at any level that you're at. If that's the kind of nominal, each sample is actually dynamically at 23 bits precision. So it's really, like, trying to think about it in terms of a regular voltage is really difficult to conceptualize. Even for me, I kind of think, because I think of it as everything kind of at the same level, and you're dealing with that. But every single sample has a dynamic range scaling and 23 bits of precision. So I would like to really get some null tests going and see how much difference there actually is that would be audible. And I mean, I'm sure there are examples that you could do that would highlight problems. Most of the time, I don't think it's going to be an issue, especially if you're using a 64-bit accumulator. In other words, you have a running total at a higher precision, and then once you've summed all that you want, you then write it back to a lower precision, and then say the end thing is just a single, either 24-bit or 32-bit floating point file. So that's the end result. And if you can hear the difference in that, then that's already that thing. Like, it's not like some actual voltage or anything else. The summing's done. It should be still, that should be about it. So I think that for most people, the limiting factor of their sound is not going to be the summing engine.
That's what I think too. I think it's a complete non-issue from what I've heard anyway. Like, I mean, I bought into this shit for like a week back in the day, and I was like, oh shit, maybe the summing in Cubase is better, and then like went and rendered stems out of Ableton and put them in Cubase and rendered them out, and I was like, sounds exactly the ssame to me. And then I like said some shit on a forum, and then someone was like, well, that's because you rendered the stem out of Ableton in the first place, and like all this shit.
Oh gosh. Well, I mean, you should just be able to take the final file of all those different processes and subtract them from each other, especially if you need to disable everything. So I think, actually this is one of the reasons that Ableton, I think, were, they actually looked into all this and they asked me about it, and they did null tests of just the straight summing. And they said, look, we can't, maybe there's 1 bit or 2 bits of that floating point number which are slightly different, but That's only on the odd sample here and there, and it's not going to actually make an audible difference. What I think is happening is people could hear the difference because of things like EQ8 not sounding good. Too. And so, but if you just do the raw summing, no processing, then I don't think that was the problem.
I don't think so either. I think the problem was a mixture of GUI based and native tools based. I think certain GUIs will make you gravitate towards certain actions, and I think that certain native devices which are easy to grab and you know that they're low CPU and they just quickly do the job you want to do get used over and over again in sessions, and that has a definite cumulative
effect. It adds up. Yeah, for sure. Yeah, I would I agree with you there. I think that's definitely what, and people I just like to say, reinforce that people can hear the differences. I don't think the differences are caused by what they think they are, is the thing. Yeah, 100%. So I'm not discounting anyone's opinion. They go, but I can clearly hear the difference. I'm like, yeah, I agree with you, but I don't think that the test was very scientific in the first place. And maybe if you think it's the summing, let's just look at that in isolation and see what the results are.
Yep, 100%. So with DSP equations, like let's say your SVF filters, you said they're doing a calculation for the sample before them or some samples before them plus the current sample, or sorry,
that's right.
Yeah. And so that must mean if you're working at 44K that this equation is being done 88,000 times a second.
Oh, no. It's okay, I see how you could think that. But what happens is, for a linear equation, so that's the simplest to solve, you have the previous state of the capacitor, some energy that it's already got stored in it. There is an input sample, a new voltage comes in, and then based on the value of that capacitor and the amount of current being pushed into it by the cutoff frequency, which the cutoff frequency as well for that sample, right? Because you have to be told what the cutoff is. Then due to the conductance of the capacitor what it will charge up to at this sample. And so you can solve for all of that straight away in one what I call it, one tick or one processing chunk. But if you've changed the cutoff, you'll need a division to cook your to recompute the accurate coefficients that will give you the right result for that implicit solving.
So the equation only happens again once the cutoff is changed.
Yeah, that's right. For a linear, for the linear state variable filter, that'll be the damping, which is the resonance, which is the Q, and the cutoff, and the mixing parameters, but they're kind of like at the output. You get all the outputs at once from a state variable filter, and you can mix them however you choose. So so that's the linear case. You can solve it in one step, but if you change any of the things, the cutoff or the resonance, you need a division to compute that. So it's like, in the line equation, y equals mx plus b, you change the m, you've got a division by m. That's all there is. But once you've changed the m, if you're using the same m next time, then you don't have to do that division. You can just store 1 on m and then multiply by that. So that's the easiest case. When it comes to nonlinear stuff, then you've got to do each nonlinearity has its own division. Each cutoff change or any gain change, if you imagine a nonlinearity is turning the volume down on the sample, any gain change like that, and some other edge cases, needs a division. Sometimes you can pull them together, but what happens is when you're solving these things, you have to iterate to a solution, because solving the nonlinear equations is too complicated directly. There's no closed form solution. You can't just get like in high school, there's the quadratic equation and it's a nonlinear thing. You get the output straight away. For those simple cases, you can have what's called an analytic solution, like this one step, and that's the answer. In general, that doesn't happen. You need to, for each sample, loop multiple times, converging towards, so you kind of bounce around, where's the zero? There it is. and it could vary depending on the input sample, the cutoff, and everything, how many times you need to repeat that loop with multiple divisions, one per nonlinearity, to then hone in on the actual solution for that sample. And then you increment all the energy of your capacitors and then process the next sample. So yeah, you could, in some tricky circuits, you're doing that iterative, it's called Newton-Raphson or modified Newton-Raphson, which is pretty crazy because Newton, you've probably heard of him, and he was around a while ago. And all of these Newton's method, or trapezoidal, he invented as well. And this is the stuff we're using to solve these circuits today. And this is pen and paper, quill and paper stuff. This was invented a long time ago. So it's kind of crazy that it's only now really a thing for real-time audio production. But yeah, it's 20. So if it's linear, one step, one set of divisions, depending on how many gain factors you're changing. If it's nonlinear, one division per nonlinearity, up to 24 times per sample. And that gives you, worst case, like 1 million sets of multiple divisions per sample to get a really accurate solution. And so obviously you're trying to minimize those number of iterative steps to get to the solution, but that's really hard.
Yeah, it's kind of wild. Like once you start looking into this shit, you're like, man, there's a lot of computers are chugging, like they're doing a lot of work.
Yeah, but my point of view is, they're getting faster and faster, and I always try and make the most efficient. Like I don't waste CPU. I make sure every single addition, multiplication, and division is needed, and and my plugins for the level of detail they're delivering are insanely low CPU, but that still can add up to for something like the latest plug-in the Scream, which is a full circuit model of an analog Ibanez tube screamer pedal. And you can adjust everything. You can adjust the slew rate on the op amps. You can swap diodes for LEDs. You can do anything you want. But then, it's taking around, for a really intense simulation, maybe 5%, 6% of a M1 kind of core. But that's fine. I think that's fine. Like for that detailed sound.
So if it's taking up 5 or 6%, does that mean you could only have like 20 of them open max before using 100%?
On one core of the
like
chip.
on one
of the CPU cores. So you could have
because there's a lot of cores.
Yeah. So each processor has like 8 cores. So 8 times. I try and aim for maximum like 10% CPU usage for a plugin.
So you're saying I could have 100 open?
Yeah, I think that's fine, right? For the most detailed tube screamer emulation that there exists. So I'm kind of aiming at that level. And I always try and provide a lower CPU option where it doesn't have all that detail. So down around the 2%. So when you don't need the detail, sure, switch it off. And then also an option where you can, so I call this, these kind of different details, like the medium definition, like the basic definition, or like SD, MD, HD, and then like UHD, trying to make it like video so that people can understand it. And I try and stick to the MD and HD. That's the kind of sweet spot. And the filters in, so the glue compressor as it is like an MD level one. It was written around like 16 years ago now. And that was still pushing the CPU, at that time. That was still a little, raising the needle a bit. But I'm currently writing the Glue version 2, which is the HD version, like based on all the latest tech that I've got going to solve these systems as really large, complicated systems efficiently.
So obviously, you love math. I mean, I don't think you could do what you do unless you like really enjoyed it.
Yeah, definitely.
Like whenever I look at math, it's like when I start looking at lately, for instance, I've been trying to build an audio feature extractor so I can train an audio classification model. And like as soon as I start looking into these equations for how to like get the centroid or the skewness or the flatness of a sound or something like that, my eyes just glaze over and I go, fuck, I don't know what the fuck I'm doing. But What was
Look,
the
I have those
moment?
days too. It's I think it's like sometimes it's got quite a high situational awareness to actually work out these equations properly. Like I glaze over it. I can look at equations in a paper and just glaze over and just go, what the heck? And you have to just chip away at it and go real slow. And when it's a new skill that you're learning, you have to be kind to yourself. And some days you're just not up for it. There's too much cognitive load. You're just like, you could waste all that time in frustration, not getting anywhere, or you could just go for a walk or do something else and then be way happier. And then when you're finally ready for it, then do it. And so, yeah, I think, be kind to yourself and know that, and chip away just at a little bit of the problem. And then get that happening, because that's what I have to do with some stuff. I'm actually doing some of that work right now where it's just like, oh, geez, I just opened like a can of worms. What's that? No, the actual like that. I look at
heavy math stuff.
Heavy for me, and I just go, whoa, all right.
Can you talk about like what is the end goal for looking at that heavy math at the moment? Can you say?
Yeah, for sure. So this is so at the moment. So I've written a circuit solver, the Cytomic circuit solver. I've called it, really catchy name. And the latest thing that I'm doing with it is when you're kind of coding these things, Dave Gamble was on the other day talking about, when you're typing in these nodes and how kind of like error prone it is and frustrating because it's not like actually the circuit. You're just like dealing with kind of code. So I've written a layer which I can use a program called LT Spice, which allows you to draw the circuit. And so I spent the last, it was about a month ago, I think I finished that work where I could draw the circuit, generate the output file, which is like the one that I would code, right? So the actual nodes and where they all are. But this circuit simulator program generates that file for me, and I just draw the circuit. And then I generate code from that. So then suddenly I can already simulate it, make sure it all works in this program. So that when I export it, then I know if it doesn't work, it's my problem. Like I've screwed up somewhere.
But it generates code. So like you draw the circuit, you click a button, it generates code for the output.
So I've written the code generator. So it generates what's called a netlist, which is each device, all the parameters of that device, and then how these devices are connected, which nodes. So if you imagine like a wire in a circuit and you have a resistor and you want to connect it to a capacitor, then you call this like node 2 or something. And then so you have R1, which could be this one, and then a space, and then 2,3 would mean it's connected to node 2 and node 3. And so you get this text file out, which is the specification of the circuit. And then Spice programs parse that and then simulate the circuit. And that's like these offline heavy circuit simulation programs that then draw plots for you or do spectral analysis or allow you to design circuits and test them virtually. So what I'm trying to do is replicate that output, replicate the simulation output, but with highly optimized code that's automatically generated from that netlist. And that way I cut out all the error proneness of trying to type that netlist in yourself, which is like not that much fun. So I've gotten up to that, like I'm doing that. And then there's another layer, which is subcircuits, where you can have a little drawing, which then you can kind of copy and paste in, but you don't have to do the manual copy and paste. You can just say, I want to use that subcircuit here, that subcircuit here, and it does all the copy and paste for you. So I've done that bit of code, which is great because that speeds everything up. And the thing that I'm currently modeling, which is why the pain, is what's called an op-amp macro model. So in other words, inside a single, in an analog circuit, you have a little component, a little chip, integrated circuit called an op-amp. And it's a complicated little beast with probably about 16 transistors in there, all doing their thing. But if you modeled each one, most of them aren't doing much. So you can kind of replace them with idealized components that just provide a little bit of current here or mirror a current over there or just do something fairly ideal. And all you need to do is model like the big stuff. So the input stage, which has a couple of transistors. If you want that much detail, sometimes you can even skip that. Current limiting. So in other words, in circuits, you've got this, it's a physical thing. You can't just generate infinite current or infinite voltage. There are limits to how much it can output in terms of current, which is like, if you imagine a river, like how fast the water is going, and then the voltage, which is kind of the volume of the water. And there are limits. So the power supply of the circuit gives you the voltage limits, and then the particular circuit and the components give you the current limits. And so you have to generate a physically realistic op amp. And in the modeling of that, I've got a good model of some transistors, but there's a particular transistor which is difficult to get a better model of, called a junction field effect transistor, which is a JFET, which and they, because they're fields, there's not there's no actual bit of wire or a semiconductor like a diode that's like actual conducting directly. There's a gap and there's a field which transmits the energy. And they happen to be a bit smoother and a bit kind of more, rounded, and they're more difficult to model with basic equations, which some of the other components aren't. They're just quite straightforward with basic versions of what that thing does. So yeah, and there's actually a guy from Sydney that wrote this paper back in the 90s, a really detailed model, which is probably too much detail for what I need. I need to cut it away and just have the kind of core that you can hear, called Parker. That's his name. So thank you very much, Mr. Parker, for writing an excellent mathematical paper on how to model this stuff properly. I much appreciate it, but it's still hard.
Right. Yeah, I imagine. Yeah, I've been, like I said, recently kind of getting into coding stuff a little bit, and it's what I'm realizing more and more is like 90% of the job is building these intermediate tools to help you get to the end result you want to get to. Like I originally like had this idea. I'm like, all right, cool. I'm going to sit down and build this idea. And then I'm like, fuck, there is so much data to process. I need to understand this part and this part and this part. And I have to build like little intermediate tools to like graph some shit here so I can see exactly what it's doing. And then like, yeah.
There is that. There are those debugging kind of things, like visualization tools. So you can debug the algorithm. And that's a part of it. But I mean, are you just talking about the DSP still? Like, so I mean,
I'm just talking about programming in general.
In general, yeah. It can get quite. I mean,
it feels like I'm constantly just building these little bespoke tools to help me with extremely specific problems that I'm having to my final goal problem.
Yeah, I mean that happens, and you can. But the good thing is, once you've written that tool, it doesn't go away. You can just keep on reusing it. Yeah, I mean, and I should probably say on that there are lots of really handy. If it's just like not processing, you don't have to make it super optimized. There are lots of existing libraries that can do certain tasks for you, and the easiest way to call them would be through a programming language called Python.
Yeah,
it has. Yeah, so you've got so many libraries, SciPy, NumPy, and they all hook into really useful processing things that you can, really save you a lot of time. But you still got to write that little script that does something.
Yeah, for example, the problem with what I'm doing right now,
what are you up to?
Well, I'm just trying to build an audio classifier using light GBM, so machine learning.
Yeah.
But to do that, I need to get a bunch of spectral features out and then feed that into
low-level processing kind of stuff, like the spectral features, feed to the LLM.
Exactly. So I just need to represent, and I just need to represent all of the audio files that I want to train it on as numbers, like a giant array of numbers, basically. So you'll have like the centroid, like where the center of gravity is. Like if you looked at a linear spectrum, like where you could put your finger and balance the spectrum.
Yeah.
And then you've got your spread, which is like how much plus or minus spread there is from that centroid. And then you've got the roll-off, which is where 85% of the energy lives below. And then you've got like your linear spectrum, which is just an array of floating point numbers. And then you've got like your kurtosis, which is how peaky or flat it is, and all this kind of stuff. So it's like you just have to do a lot of getting numbers. And what I've found is I've been using tools to try and get these numbers, like Essentia and Orbio and Mida and Labrosa, for example, is one of them. And the numbers are completely different for all of them. Like I'll run the same sample through Essentia and it'll say, oh, this has a centroid of 12 million hertz. And I'll be like, okay.
Maybe
and
not.
then I'll run it through like Orbio and it'll say, oh, the spectral spread of this is 25,000 hertz. It's like, it's not possible. So, so I've been trying to get those numbers myself without relying on a library, because I just don't trust them after seeing some of these numbers.
That's pretty crazy. I do wonder if they aren't parsing the sample rate correctly, or they're doing something else weird.
Something like that, or they're not doing like Nyquist divided by 2, so they're taking a bunch of the useless bins from the second half of the spectrum or something like that.
Yeah, weird. The other thing that jumps to mind with that kind of thing is that a lot of the time, say when you've got a time stretching algorithm, like it's called, there's the standard one, which is noise, sines, and transients, which is a decomposition of an audio wave into these components. And there are, I think, existing kind of free libraries that can do time stretching like that. But instead of just stretching the thing, you could use those as like the audio features, or as part of those audio features to help you give the neural network some solid numbers to crunch on to characterize something. So I don't know if that I do DSP. I specialize in analog modeling, not in feature extraction or anything else like that.
Yeah, well, the first thing I tried was just like batch extracting tons of shit with Labrosa, and then trying to feed those numbers to a model. And the result was that the model was worse than random at guessing what a thing is. So there's a number for LightGBM. It's 0.693 is like where the efficacy is considered to be random, and then anything above 0.693 is considered worse than random. And I was getting results like 0.8, so way worse than random. But after I've been extracting the features myself, now I've got it down to like 0.15, which is like it's guessing like 80%, 90% of the time.
Oh, okay. So well done for making progress. That's good. It is. Things are really, that kind of side of things in terms of neural network training, I think is getting really interesting. And I don't think it's going to, I'm pretty sure that in my space, which is, doing these very much white box, I'm concentrating on the details of each component and getting a solid simulation for that, but super fast. I'm not sure how much these kind of technologies are going to improve that, but they might actually help with the actual component model. So if you've got some of the components, the magnetic fields are really complicated, the interactions and memory, and if you can isolate even consider a vacuum tube, an old tube, right? And you've got these 3 connections, and it's quite dynamic. There's memory effects that happen, hysteresis in the magnetic fields that exist in these devices that make them kind of behave in a slow and dynamic way that's really pleasing to the ear. They're complicated little beasties. And I could see applying some kind of AI model to actually characterize. So you like that's the black box, just the one component. And that's isolated all of the everything to just that one thing. I think as a total black box where you've got hundreds of components, that are all doing complicated things, that's a bit much to ask of a characterization system like that. You're not going to get results when you push things hard that will bend nicely, just like the analog circuit. But one device, I think that could probably work. But
and what kind of? Oh, sorry, go on.
Yeah, but then the problem with that is the cache, the memory. Like what makes computers slow, or a lot of algorithms slow, isn't the number crunching, like I'm talking looping 24 times for one sample with lots of divisions. As long as you're not accessing that much memory, that's all super fast. As soon as when with AI inference, you've got huge amounts of memory that you're trying to pull. And when people are running benchmarks, the limiting factor is memory bandwidth. And the same thing will happen if you're doing circuit simulation. I've tried to do lookup tables to pre-compute stuff, and it ends up being slower. So fewer of those iterative steps, but you're just sitting around twiddling your thumbs waiting for that memory to come in from because it's not in the cache, and that causes more of a stutter than just intense tight loop processing of lots of numbers.
And what kind of numbers would you be trying? So all machine learning is trained on just giant spreadsheets of numbers, basically. So like what kind of numbers would you be getting out of, say, a transistor? Like in my case, for digital audio files, it's stuff like centroid, roll-off, spread, kurtosis. Would it be like still similar to it? Like you get like a centroid, or would you get like an amount of noise versus whatever? Or
so it would be you have I think you're like using like you would do in generating test plots in a data sheet. So you hold some pins constant and then you sweep like some of the other pins, and then it makes a certain shape and then train it to reproduce that shape. So I think you could be pretty direct with, I don't think you'd have to feature extract. These curves are kind of like fairly smooth and they do a certain thing, but
how many points would you need on that curve? Because I mean, like, would you need all 22,000 points, or do you think you could, like for analog gear, or do you think you could whittle it down to like 128 points for that curve?
Oh, that would be 128, I think would be fine. If the neural network could do the smooth, like a kind of a C2 smooth interpolation in its inference. In other words, if it would have a continuous function, a continuous first derivative and second derivative of the function, if it could output smooth enough stuff, or you could artificially smooth the outputs so that they would behave really nicely, then yeah, I don't think you'd need that many points to train on. But I don't know how continuity works when you're doing a curve fit. So there are certain numerical approximations that you need to use, and even like the power function, like a maths function, I have to write my own versions of, which are highly optimized, and I'm really careful to smooth the endpoints. So when you stitch together two sections, they're smooth transitions between them. I have no idea what neural networks do with regards to continuity of function approximations. So I think they could be trained to be smooth, but it might need some other constraints which aren't like mainstream things, because audio is just different.
The resolution is really high.
It's just so different to vision. Like there's a bunch of video generators and stuff, and you can get away with some blurs and some jumps and whatever, it's fine. But in audio, you're like, ooh, what's that weird click or something? What the hell? This is unusable. So.
Yeah, exactly. Or like a lot of the AI currently has all these spectral artifacts, probably because it was trained on shitloads of MP3 or something.
Yeah, exactly.
Or trained on all of Spotify's data. It might be even worse. Maybe it's trained on like 64 Opus or something.
Yeah, I'm still waiting for the fall, the copyright. Like, where is this going to fall?
The UDO Suno case with the RMCC or RIAA or whatever it's called.
Yeah, there's just so many cases going on. It's such a wild west of like a hypocrisy and litigation and just blatant copyright infringement. I mean, we thought, the old Napster or whatever was bad, and this is just different level bad. This is like people's personal conversations being
Right.
mined. It's like, it's just crazy. Yeah.
And the justification for it is so funny too. They're like, well, it would be the same if a human went and listened to all 2 billion songs on Spotify.
Okay, yeah.
and
Let's
got
guess how many humans can do that. Seriously,
Yeah,
it's
exactly.
totally not the same. You're just
Like exact same.
get your
like,
hand off it.
Yeah.
It's so ridiculous. So, but the hypocrisy of this sort of stuff was that one of the services, I can't remember, got hit with some of these copyright things, and they're like, oh, it doesn't matter. And then somebody started training their stuff on the output of their thing, and then they got all worried about it. You can't do that. It's illegal to train off our stuff.
Yeah, it was DeepSeek R1, which used a process called. There's a process called distillation.
Distillation, which I think is brilliant. Hats off to those guys. Nice work. Brilliant.
Yeah, for those who don't know, distillation is where you basically get like there's sort of a teacher-trainer relationship between 2 models, where a big model like ChatGPT will distill its knowledge into a smaller model like DeepSeek R1, and OpenAI got all butthurt about that.
Sucks to be you. I feel so. We need those memes with all the tinsy little violins, the little tardigrade playing a violin.
Right. So, I'm curious to ask. You've talked about modeling analog gear not by emulating the surface behavior of it, but by solving the actual equations from the circuit. Why is this so important to you?
It just sounds good. It's like physically realistic. You are reproducing all the limits of the actual analog circuit. You can't. Everything kind of bends when you push it hard, and I push it hard. Like I slam my models with like huge signals and like ridiculous frequency modulation, and I want them to be smooth. I mean, some things in digital aren't, but the results just speak for themselves. And it's not like even, you can idealize it, so you can take away some of these limits. But okay, so maybe the best way was this, to describe it was this. Inside Ableton, so they licensed not just the glue, but there's another product called the Drop, which I've done, and it has a bunch of really intensely modeled resonant filters from different synthesizers. So everything from MS-20 Mark 1, Mark 2, Moog Prodigy, Oscar. And one of my favorite ones that I've got in there is actually this guy, Osamu, a Japanese guy that doesn't even do audio for a living. He's just an engineer that reverse engineered the Oscar filter, but then made it more general. And so this is an input mixing one. I'm getting distracted here, but I'll get back to it. It's like a state variable filter that you send into it the signal that you want high passed, and then in a different place you send in a signal that you want band passed, and then in a different place you send in a signal that you want low passed, and then it does that filtering and then get a single output, which is crazy. And this is the OSR filter in no, it's a different one. It's only in the Drop. But anyway, so I was in Berlin at the Ableton offices, and we're talking about the different filters to license which has already happened, ages ago now. And we're looking at different levels of filtered detail. So in other words, I've got loads of nonlinearities in each of these filters, but that takes processor. So what does it sound like if you just skip some of them? Like, let's just take out the detail. What's the difference? And it was interesting to do. So it took a little bit of time because I hadn't automated the process as much as I have now. But I listened to the full model, and it sounded kind of rounded, and so we modulated it. We played, had it mapped to a knob, and we kind of tweaked it out and just had a listen, and it sounded kind of rounded and nice. And then we took away a nonlinearity and then played with it. It was close, but it sounded just a little bit, I wouldn't say harsher, but maybe just brighter, a little bit less rounded. And then took away some more, and it started just getting brighter and clearly more digital. Like it was still you could modulate it fast. It still sounded great, but it didn't quite have that. When you turn the knob and when you increase the signal level, it just kind of starts driving, but in a smooth kind of way. Everything became more sudden and less smooth. And the CPU was down, but suddenly you kind of lost that vibe, and you've just got like a sterile EQ kind of filter. And yeah, that was an interesting exercise, and that really reinforced that, when we were talking about before how people's songs with tinsy little, cuts to them with bad processing added up to a really bad sounding song. Well, this is kind of the opposite. Each of these little non-linearities, each of the little bits of filtering, a little bit of drive, a little bit more filtering, a little bit more drive, and then some feedback, and then some harsher distortion here. But each of these little stages all adds up, and it makes a difference. You can hear it in how the cutoff kind of self-modulates itself against the audio signal, in how complicated and pleasing the whole thing is. And that just kind of re-emphasized how much all of this stuff actually matters, and every single little bit of some processing going on that does anything to the sound actually all adds up and is important to model with as little CPU as you can, but to get the detail of the final thing to be as close as you can to the actual circuit. And you can hear the difference. Like you can A/B like between different people. Love their filters, and it's an easy example, I think, especially with us kind of synth heads and people that love filtering and distorting stuff. People always go, oh yeah, but it doesn't sound analog. And it's like, yeah, a lot of this stuff doesn't, but I'm really working on making it really, really analog sounding.
What's your personal criteria for when emulating a piece of gear becomes meaningful, and when do you think it becomes mimicry for mimicry's sake?
Yeah.
Surely there's a cutoff, right, to where like you're not really hearing the difference, but you just want it to be exact or something.
Yeah, there's sometimes I think looking at an oscilloscope signal sometimes is more, you can see more differences than you can hear. And even looking at a spectrum, there are some times when, so I always like to have options. So if there is something that's doing something meaningful to the behavior, so that it's like when you've turned the knobs to this, it actually does something fundamentally different, then I try and capture that. And if that thing takes loads of CPU, then I just leave that for the HD version. And then, if people don't need it that accurate, then you've got the MD version, and you can switch to the HD one on render. So I've got an option in the plugin, so you can switch over sampling. So if you need to offload the CPU, but you want a really good quality render, you can just use 16 times oversampling, 32 times oversampling only on the render. And it automatically adjusts all the latency and does everything for you all perfectly. And you've got a pristine bounced result. And then you can mix with that in your, you just bounce that track down and then mix with that. And the same with the HD, you can switch to this HD mode on render. So I am pretty liberal with the CPU that I'll spend to capture a little nuanced detail. And I like making a video of that then. I'm like, here you go, this is the analog circuit, and, costs a bit of CPU, but hey, it matches really well. If I can't see it and I can't hear it, then I can't model it. So I'm sure there's some levels of things that I'm missing, or, if the shape's off by a little bit, but it still kind of sounds the same, I'm not going in and measuring every single resistor to get 100% match. It's 99%, and the difference between what I'm doing and two different builds of the same circuit, the resistor will be a different value anyway. It's like, am I matching that circuit, or am I matching these circuits? So yeah, I do like to probably push the boat out a lot more than a lot of other developers, because in 10 years' time, this is going to be the standard thing that people will use. And I've already moved on to even using more CPU later on. I'm aiming for the plugins to be around for at least 10 years and for them to be in their prime during that whole time. And they'll be a little ouchy at the start, and then people will be adding them on every track towards the end.
It's a good way to look at it.
yeah, like and with this HD on render, with oversampling on render, I take these cues from the 3D industry where they have render, right? Who would use the preview output of a 3D package as the final thing? I mean, maybe in Blender with Eevee or one of the, like, they're actually getting pretty good, or Unreal Engine with some of the Star Wars scenes, they're actually getting pretty good, but that just kills the whole system. They've got multiple GPUs rendering that in real time for that film feature production, and they need the real-time viz so that they can do the acting. Not many producers have that, so it's even more important like to have these options for higher quality on render. I think you don't have to use them.
Yeah, 100%. Do you think there's like a holy grail circuit or a device that you still don't think has been accurately captured in the plugin world?
I mean,
other than you mentioned the JFET earlier,
the JFET. So I mean,
tape is like a hard one as well that I feel like people haven't really gotten right yet. Maybe
the which? Sorry,
tape
saturation. I'm not an expert on that. I think there's some good progress on that. Like there are some people doing physical models of tape, and they're randomizing the position of the grains and trying to model the magnetic field as a whole, as an emergent sum of as the tape head goes over. So, but I'll take your word for it that they're still not really there yet. I think that's definitely. I think it comes down to these magnetic fields. So anytime you have a field and things can be a bit, round, harder to simulate with direct equations.
Yeah, when you've got these random and nonlinear.
Yeah, they're a bit more complicated because the spatial side of things comes in, I think. So, so SPICE, this standard circuit simulation stuff, doesn't really model space. So if you have a component next to another one, or on the other side of the schematic when you draw it, the wire, gesticulating, when you have a component close or further away on the schematic, it's the same thing in the end simulation. There's no notion of how long the wire is. And doing spatial modeling starts getting really computationally heavy. And they do it. When people are designing new semiconductors, they need to get it right. And they have to do it spatially. So anything that has a spatial aspect to it, or a dynamic magnetic field aspect to it. So I think tubes are still, we can do better. JFETs I think are okay. They're just complicated. So I'm just banging my head against that one. And I'm sure Dave Gamble appreciates that one for a FET compressor. So I want to do an 1176, and that has a really prominent FET right at the start. I think even there are some really good papers just coming out on nonlinear transformers, which is another magnetic field effect, nonlinear field with hysteresis. So that kind of stuff is, I think, difficult. And the other, most circuits are already difficult enough, let alone chuck that in there. So yeah, there's that. So in terms of so tape, I think maybe there's another magnetic field thing, and I'm sure there's another one. There is a really interesting set of papers, like I said before, coming out. There's something even like more complicated than what I'm currently doing, called Port Hamiltonian modeling, which I'm still like, that's one of those bang my head against things, like you're saying with these things. This is going to take me a while to get into it, but the results are looking really good, and they're tackling all these complicated systems from first principles, like doing detailed new modeling of these things. So that's like, I think, holy grail kind of territory, and then getting them done with efficiency. But there's plenty of lower hanging fruit for me to tackle in terms of even, I think, transistors. What are they called? There's a certain type of transistor in fuzz pedals which people love, germanium transistors, and they have a different response to a regular transistor, and a lot more of something called nonlinear capacitance, which is when the capacitor changes its capacitance value due to different currents and everything going on in the transistor itself. So that's another, and I've tackled that at a pretty good level. So I think I can tackle a fuzz pedal with actual accurately modeled germanium transistors. So we'll see how that goes. Talk to me in a year or two and see see what I'm saying then.
Some of the names in this space are so funny. Like you just mentioned Port Hamiltonian,
yeah,
or whatever. And the other day I was reading about shit, and I read about Wiener entropy.
Oh yeah. There's a bunch of people that first came up with something, and they got their names immortalized that everyone can mispronounce forevermore.
Yeah.
Wiener. Wine. I think it's Weiner. I don't know. Yeah.
It might be, yeah.
I don't know. I have no idea what that is.
Yeah, me either, to be honest. If you had unlimited CPU and memory, what would you build? Like if just computing power was just not a thing. You just build it.
One thing that I'm interested in is just, it would be kind of fun just to do a full circuit simulation, not a macro model where you're doing cheap op amps, but just every transistor in the whole thing, just like how as an offline render thing perhaps, or as a cloud compute thing. But I think probably some of the spatial stuff would be interesting to throw finite elements at. So you can have these models which spatially you do a 3D mesh, and you triangulate the mesh, and then at even kind of sampling points as you can, and then vibrations through the mesh happen spatially. So your sampling size has to be to do with the speed of sound at your Nyquist, above your Nyquist frequency of the speed of sound in that medium as it vibrates. So your kind of samples are the wobbling of the material. And I don't think there's been much. There are physical modeling stuff, but I mean, if you had infinite, you could just model the crap out of any vibrational system. And that would be
things like spring reverbs or something like that.
Any, like, even, violins, guitars, anything that vibrates. Drums would be interesting, like to do some really good drum modeling, like proper. You've got a drum head in front of you, and then it's an infinitely malleable digital entity that you can do what you want to. Yeah,
it's interesting the way we do that currently. It's like mostly all the physical modeling shit is just like delay lines, right? It's just all carpless.
Well, I wouldn't want to simplify it that much. I think there's been more progress than that, but yeah, a lot of it is pretty much that. So you're oversimplifying that system quite a lot. So symbols, model one symbol, like the actual, like, I don't know if but then, so there are all kinds of different vibrations that go around the symbol and then along it, and then in modes, like in quarters of different thing, and then it's all a stiff system, and the different frequencies go at different speeds. But it would be pretty cool. Could you imagine like having like this? You could hit it anywhere and like damp it anywhere, but then program that, like, to generate all kinds of really cool sounds. I mean, I kind of like that physically. I like just random synthesis that you can crunch samples and do granular stuff or do. But I think sometimes some of the complexity of a real system that has a virtuoso kind of playing it is so detailed and so intricate that being able to then automate that in ways that are inhumanly possible could lead to some really interesting results.
Right, like taking a symbol, but then just hitting it at the exact same place and the exact same velocity every single time, for example, it might end up creating some like insane resonance that a human just possibly couldn't generate because.
Well, you could hit it, you could smash it really hard that a human wouldn't be that strong. But I meant more the timing, like the actual intricate timing and muting of the symbol at any place, you could like suddenly just like mute that little place and then excite it with any excitation symbol, like at any point, and you could play a whole symphony just on one symbol. I think you could like do a physical model version of the Aphex bouncing ball and just try and just like get a whole song out of one intricately played thing. But I don't know, like maybe it'll sound terrible. I have no idea.
I mean, I'd be interested to hear it. It's a fun concept. Yeah, the math for that seems like it would just be off the charts complicated.
I think the maths is pretty well understood, and this is why you said, when you had infinite processing, I think it's just actually really computationally expensive that people don't do it. But if you had suddenly, like huge amounts of compute that became like trivial, then yeah, sure, then it's all on.
Well, here's maybe a different way to phrase that question is, what's one problem in DSP that you think about often that hasn't been solved yet?
Yeah. I think a lot of the stuff has been solved. It's just not practical. So I think that where, it's kind of like the Schrodinger equation. It's something that has been, we know the equation, but solving it with the amount of compute that we have just isn't really possible. So it's not like the theory is not there, but I think it just comes back to the magnetic core type stuff, nonlinear saturating magnetic field interaction stuff, which is complicated. So yeah, and I haven't really spent much time trying to solve it as well and seeing how much CPU it takes and how complicated it is. But I think when you've got systems which kind of the system changes in non-trivial ways with these hysteresis memory components which change the saturation curves and do different things, I think that's where we can still, kind of do better and get a more accurate solution. But then perhaps even the other side of things where there's intersections between electromechanical systems, but and you could probably get some good results for that. But I'm fine with people still having an amp and a speaker and it having a valve in it, and that you can just stick a mic in front because it sounds good. We don't need to model everything, I don't think.
Right. Yeah. Yeah, that makes sense. Well, thanks a lot for coming on the podcast and chatting. It was really interesting to hear your take on a lot of this stuff. And yeah, it was nice to actually connect.
No, it was, thank you very much for having me. Oh, and before I go, I have to do a shout out, if that's all right.
Yeah, absolutely.
To my friend Aaron G. Style and Tracy, who got me onto your podcast and got me to listen to your music. So I'm very thankful for that. And also, I think a shout out to the Alliance crew that they're with, which are some guys here in Perth that really love their music and have great parties and great music producers. So, hi guys, and thank you very much for having me. And thank you for your music and your podcast for taking all the time and care and attention to everything that you do.
Yeah, of course. And where's the best place for people to go to find your work? I know you've got a lot of papers on your website and plugins and whatnot.
Yeah, so if you go to cytomic.com, cytomic.com, and there's a link to technical papers. And if anyone wants to know more about so if you want to implement your own Ableton EQ filter, then the paper's there. You can do it. If you're into programming, it'll take you an afternoon and you can process some signals. There's a talk that I gave at the Audio Developer Conference 2020 on more of the trickier nonlinear stuff with lots of diagrams and things, and that's a YouTube of that as well, but that's all linked from that page. And that's the technical side of things. And then I'm hanging around on KVR and Gearspace, so you can pop questions to me, and my direct email's on the webpage too, so fire me off a question and if you've got it. And a lot of people they've thanked me for that SVF paper and some of the other papers I've written, and I think that's the best way to kind of go when it comes to sharing this information and making it because you're giving them the why, not just the here's the thing that does it. This is why, this is how it got there to do it. So then they can learn and do their own thing, which I think sometimes open source doesn't give you, because then there's just the code, and that's good in some ways, but the paper with the explanation of the code is even better.
Yeah, agreed. Yeah, I was surprised to see that on your website when I was looking into this podcast. I was like, shit, there's like information about how to do literally everything you do here. That's crazy.
Yeah, so I don't like patents or and the whole BS that has turned into this game of sharing information but then coding it in ways that it's almost impenetrable, so that then you can get legal against somebody for trying to infringe something. The whole point of the patent system was to share information, not kind of and protect your IP a bit. But I think the better way is trickle it out after it's not, totally your core IP that you need to push the next product or, innovate. It's like the slightly older stuff that everyone could benefit from. Maybe just give that away and be nice about it.
Yeah, it makes sense to me. Well, thanks again, man. I appreciate it.
Yeah, thanks so much. Great to chat.